Good afternoon, everybody. Welcome to what is going to be the final past seminar of the fall semester in our first semester of running this past seminar series. We will continue to have a series during spring. Um, it'll probably be on Tuesdays, and look out in spring semester for announcements about speakers and their topics. So I want to get right into today's speaker, MirSaleh Bahavarnia, who comes to us from Vanderbilt University, where he's a postdoc. And let me tell you how this talk came to be, because it came to be from Twitter. Specifically, maybe you know this, MirSaleh, that his postdoctoral advisor, Ahmed Taha, who works in the controls area and works on distributed controls and has done interesting things in power systems. I've admired his work for some years, and I think he was at UT.
San Antonio.
Yeah, UT San Antonio, MirSaleh.
Yeah, exactly.
And were you there with him?
No, actually, I joined his research group when he was at Vanderbilt University. I joined at 2022.
Got it. So he recently moved to Vanderbilt, and some of you know some folks at Vanderbilt. They've been assembling some very interesting folks there. And anyways, Ahmad Taha posted this paper that MirSaleh wrote with this great title, "How many autonomous vehicles are required to stabilize traffic flow?" And I thought, "Ooh, this is super interesting." And I knew it'd be interesting to many people here. So I asked if they could share it with us. And so MirSaleh was kind enough to accept the invite. MirSaleh himself got bachelor's at Sharif University Technology, according to LinkedIn, and PhD at Lehigh, and I guess we just learned started postdoc at Vanderbilt with Professor Mataha. And
Actually,
anyways,
prior to this postdoc, I was a postdoc at University of Maryland with Professor Nuno Martins for one
ah,
and a half year.
excellent,
Yeah,
excellent. So
this is my second postdoc. Yeah,
it's a pleasure to have you, and the floor is yours.
exactly. So, can I start?
Please.
Okay, okay. So let me share my desktop with you. Okay, so can you see the slides?
Yes.
Okay, perfect.
If you could full screen it, it'd be a little better.
Okay, so I will also post it later on. I will email it to you so that you could share. I mean, is it okay?
Yeah, can you hit Control or Command L?
Command. Uh, oh, you mean full screen?
Yes.
Okay, okay, perfect. So hello everyone. Good afternoon. Thank you so much for attending my presentation. It's my great pleasure to share our latest research results with you today. Thank you so much, Professor Mora, for introducing me and inviting me to this great talk. So it would be my pleasure to give the details about our research to you today. So as you mentioned, the title of our recent research is How many autonomous vehicles are required to stabilize traffic flow? Actually, we will consider some sort of idealized conditions, like when we do not have any noise. So definitely for deriving mathematical results for the first step, we need to, assume some simplifying assumptions. Hopefully, in the next step, we would be able to generalize these results to those more realistic scenarios as well. So this is a joint research work with my postdoc advisor, Professor Ahmed Taha, as you see here, alongside my picture. So let's get started. So here is the outline of my presentation. First of all, I will go through the main concepts, and then I will, include a few related literature works in the literature, actually, and then I will explain the motivating points.
Your slides aren't progressing for some reason. It's still stuck on the title slide.
Actually, now it should be on second slide. So,
Can you unshare and then reshare your screen?
oh, okay. Sorry about that. So hopefully now you can see this the second slide. Okay, cool. So yeah, as I mentioned, first of all, I will go through the main concepts and some highly related works and providing some motivations why we have actually explored this problem and studied it deeply. And then I will give a list of main contributions of this work. In the second part, I will go through the dynamics of the human-driven vehicles and also the autonomous vehicles. And after that, I will formally state the problem to be investigated. And in the third section, first of all, we will go through the necessary and sufficient conditions for the satisfaction of the string stability criterion that we will introduce. After that, I will show how to parameterize the constraint sets defined by the rational driving constraints and box constraints on the controller parameters. And finally, I will provide the theoretical results showcasing the derivation of optimal lower bound on the AV penetration rate, the ratio of the number of autonomous vehicles to the number of total vehicles. And some numerical simulations will illustrate the effectiveness of our theoretical results. Finally, I will conclude with a few concluding remarks and drawing some future directions. So here in this picture, you see the experimental verification of the traffic flow stabilization via a single AV, the experiment done by Stern et al. In 2018. So here in the first upper picture, you see the equidistant 21 vehicles in a circular experiment that in the second picture, you see some, stop and go waves happening here due to the collective behavior of the human-driven vehicles. In order to smooth the stop and go waves and improve the total vehicle fuel consumption and emissions, just a single AV autonomous vehicle is employed to stabilize the traffic flow dynamics. As you see, again, we see some sort of equidistant vehicles on the road. So in order to mathematically investigate this problem, we need to consider some models. So the main model considered in the literature is the simple car following models. It could be either nonlinear or linearized ones. And main stability notions here are twofold: string stability and local stability. By string stability, we mean that when we have perturbation input, we wanna that perturbation be dampened through the flow. So the equivalent interpretation would be we should have no increasing or unstable modes, meaning that infinitesimal perturbations should not get amplified. One famous mathematical idea to impose this string stability is simply imposing the H infinity norm of the uh, closed loop be less than or equal to 1. As you know, when we have a transfer function from input to output, when we impose the norm of that block, that transfer function, then the norm, H infinity norm, or any other norm, here we consider the H infinity norm, specifically for dampening the perturbations. When we impose the norm would be less than 1, then we have some consecutive blocks, then the multiplication would be also less than 1. So um, the norm of the output would be smaller than the norm of the input. That's why we say that perturbation would be dampened. And with local stability, which is very usual, standard concept in the control theory, we mean having no unbounded or unstable state trajectories inside each vehicle's dynamics. So the mathematical way to impose such a stability is just considering the Hurwitz criterion and applying it actually in the continuous time. When it is the discrete time, we need to apply the Shor stability. By Hurwitz stability criterion, we mean all the poles should be on the left half plane. All of them should be stable. So here, I want to list a few highly related research works. First of all, in these two fundamental works, they have shown that the traffic flow could be stabilized via a single AV. So in the first work, actually, they have not considered any lower or upper bounds on the controller parameters. That's why they find, let's say, 10 to the power of 4 as a gain, as a scalar gain for the controller. But in the second work, in this work, actually, they somehow considered the lower and upper bounds on the controller parameters, you know, imposed by the physics of the problem. But the thing is that they did not actually systematically implement it in the problem setup. They just applied it via the numerical simulations. They considered those constraints as explicit constraints on the controller parameters in the optimization problem setup. So the other research works are somehow far from what we have considered in this paper, but let me go through them as well. So in these works, they have considered a setup, mixed vehicular platinum consisting of a single AV and multiple HVs, human-driven vehicles. And they have shown that that system is not completely controllable, but it is stabilizable. So, in other words, the uncontrollable modes are fortunately stable. And then they have shown that we can synthesize H2 optimal controllers in order to mitigate some undesirable perturbations. In these research works, they have considered general nonlinear car following dynamics, and they have proposed optimal control of AVs in order to minimize vehicle speed perturbation. And also, in the second case, they have considered the scenario that we have cyber attacks as well. So they have utilized a min-max approach in order to deal with those cyber attacks. And in this work, they have considered general functional form of car following dynamics, and they have proposed effective additive autonomous vehicle controllers in order to provide provable speed profile tracking convergence. assuming some sufficient conditions on the safety and string stability. In the continuing research works, in this work, they have done comparative analysis of 10 AV algorithms, considering various performance metrics like time to stabilize, maximum headway, vehicle miles traveled, and fuel economy. In this work, as a survey paper, you can see a comprehensive literature review of AV control. And in a recent thorough experimental study consisting of 100 vehicles, actually this work has been done in collaboration with Vanderbilt University and also UC Berkeley and probably some other universities that I do not remember right now. So it was a great work that the authors have implemented various controllers to smooth the stop and go traffic waves, and autonomous vehicles were simulated in multiple scenarios to evaluate their effectiveness on the traffic flow stabilization. And finally, as a recent work, some researchers have proposed how we can take advantage of reinforcement learning based controllers to improve the quality of traffic congestion. Hopefully this path would be some sort of new path to the classical control theory that mostly have been studied. So, as I mentioned, in the absence of noise, idealized circumstance, the traffic flow can be stabilized via a single AV, just one autonomous vehicle. But the thing is that we need to employ a high gain controller. In some scenarios, some realistic scenarios, physics-based scenarios, it is not desirable to propose such controllers. Those controllers, high gain controllers, could be, dangerous to the safety of the system. So in a more realistic scenario, we need to incorporate the controller, the lower and upper bounds on the controller gains. As I previously mentioned in this work, which is highly close to our work, in the sense that they have considered a bounded search space of the physically realizable AV controller gains, but just for the numerical simulations, not in a systematic way. So they just explicitly consider them and solve the optimization problem via some sort of brute force search method. So motivated by our other recent works that it would be presented next week by my postdoc advisor in Italy in the CDC 2024, that we had considered a constrained version of an unconstrained CAV Platon H-infinity controller synthesis problem. In this paper, we take a similar approach. We systematically incorporate the lower and upper bounds on the controllers. And also we will systematically incorporate the RDC, rational driving constraints as well. And then we would study the problem of stabilization of the traffic flow via a few number of autonomous vehicles. So we will finally compare our results with the unconstrained scenario that I mentioned in this work. So here is the research question that we propose. Motivated by the high gain controller limitation and taking into account a more realistic gain constraint scenario, as I mentioned, and motivated by our recent research work, we pose this question: can we systematically stabilize traffic flow via autonomous vehicles subject to the lower and upper bounds on the control parameters? If the answer is yes to the first part, so what is the minimum number of required autonomous vehicles to do that? So here is the summary of contributions of this paper. First of all, considering this similar scenario to the previous related research work, which was considering a single lane, no ramps, and uniform circular road. We consider a constraint version, incorporating the lower and upper bounds on the control parameters of that unconstrained problem of the stabilization of the traffic flow via autonomous vehicles. So here is the main threefold contributions of this work. First of all, we derive a necessary and sufficient condition for imposing the string stability criterion. Secondly, we parameterize the uh, constraint set consisting of the rational driving constraints, RDC, and also the box constraints, the constraints encoding the lower and upper bounds on the control parameters. And finally, we derive the optimal lower bound on the AV penetration rate. Given the number of human-driven vehicles, we would tell that at least with how many autonomous vehicles we could stabilize the traffic flow. Or equivalently with, let's say, a single AV, at most, how many human-driven vehicles could be stabilized. So we will provide a simple procedure to compute the optimal lower bound on the AV penetration rate via nonlinear optimization. And we will validate the theoretical results with illustrating examples. And also, we will introduce a notion of H-infinity-based measure to quantify the string stability quality, considering the distribution of the AVs in the circular road. Because mostly in the string stability based stabilization, they just consider the stabilization of the whole closed loop, and the methodology is blind with respect to the specific locations of the AVs. So in this work, we also employ a greedy algorithm to obtain the suboptimal distribution of the autonomous vehicles. And our guess is that it's actually intuitive guess that the distribution would be like a uniform distribution for the autonomous vehicles. So let's get started with the dynamics of the vehicles. So first of all, we consider the following ordering for the vehicles. The vehicle J plus 1 leads the vehicle J. And for the J equal to N, the vehicle N plus 1 would be defined and treated as vehicle 1. So for each human-driven vehicle, we consider the following second-order car following dynamics. So xj of t is the position along the road, L is the road length, hj is defined as the spacing between the j plus 1's vehicle and the j's vehicle. And v is the velocity, so it's the first derivative of the position, and ihv denotes the index set associated with the hvs. So one important example of these dynamics, car following dynamics, is the optimal velocity follow the leader or VFTL model. So considering the dynamics one, under small perturbations around the equilibrium, we linearize it and we get this linearized dynamics. So alpha 1, alpha 2, and alpha 3 would be our parameters for the system dynamics. And as you know, when we linearize, we would get some quantities that they are infinitesimal position difference between the, defined as the current quantity minus the equilibrium quantity for both y for position and u velocity. So we will try to stabilize these dynamics actually by utilizing the autonomous vehicles dynamics, as we will see in the next slides. So in order to impose the rational driving constraints, we can consider these standard assumptions. The acceleration of the vehicle J should be reduced when the spacing decreases or when the relative velocity decreases, and finally, when the vehicle's velocity increases. So those physical statements could be translated into these mathematical representation. Alpha 1, alpha 3 minus alpha 2, and alpha 3 could be computed via these partial differentiations at equilibrium point. So imposing these signs, positivities, would impose those rational driving constraints. And also regarding the transfer function of the system, we can simply define it with the ratio of the output corresponding to the J's vehicle with respect to the output of the J plus 1's vehicle. And by taking the Laplace transformation, we can simply get this transfer function from these dynamics. And the local stability of the system would be equivalent to satisfaction of the positivity of these parameters, alpha 1 and alpha 2, based on the Horvitz stability criteria, Routh-Horvitz, actually, standard stability. So regarding the autonomous vehicles dynamics, similarly, we would have these car following dynamics and also their linearized versions. Beta 1, beta 2, and beta 3 would be our controller parameters that we will impose the lower and upper bounds on them. So similarly, the risk aversion criteria could be imposed by these inequalities, these positivities. And similarly, the corresponding transfer function would be defined as the ratio of the output of J's vehicle to the output of the J plus 1's vehicle, the similar transfer function form. And the stability would be, again, equivalent to the satisfaction of these two simple inequalities. So let's formulate the problem to be studied here. So we will consider the mixed vehicular platoon consisting of human-driven vehicles dynamics and also the autonomous vehicles dynamics. And that mixed platoon with the linearized dynamics is said to be string stable if for the infinitesimal perturbations, we don't have amplifications and the system remains close to the equilibrium. And the mathematical definition of string stability can be stated as this. A mixed vehicular platoon with linearized dynamics is said to be string stable if all of its eigenmodes lie on the left half plane. So this is the mathematical way of imposing the string stability. And here we see the box constraints that we will impose in order to incorporate the lower and upper bounds on the control parameters. And based on the physics of the problem and also the RDC and local stability constraints, the lower bounds also automatically would be imposed to be positive. So here is the problem that we study in this paper. Given a mixed vehicular platoon with linearized dynamics, the rational driving constraints, and also the lower and upper bounds on the control parameters, vector beta, find the optimal beta star for which the traffic flow can be stabilized with an optimally minimum autonomous vehicle penetration rate. So since
MirSaleh,
Can I ask a
yes,
clarifying question?
for sure.
So the box constraints on the control parameters betas. So actually these are constraints on the dynamics of the ABs, right? Their constraints on the Jacobians related to the linearization of the AB dynamics, as opposed to like um, box constraints employed on a control law and a feedback loop. It's rather, yeah. So you're
E-
nodding. So
Exactly. Let me clarify. Good question, actually. So for the derivations in this paper, for simplicity, we have considered the box constraints on these parameters, beta 1 up to beta 3. But you are correct. If we want to consider more realistic controller setup, we need to find some sort of one-to-one mapping between these betas and the controller gains in the controller setup. That one could be implemented in the engineering implementation phase of the problem. Since in this paper it was more theoretical than implementation aspect. So for simplicity of the derivations, we have considered the imposing the lower and upper bounds on the control parameters beta. So that's the thing, actually. Okay, so here we take advantage of the periodicity of the circular road setup uh, and get this condition. You know that the multiplication of all those transfer functions would be equal to 1 because it is circular road setup. The input and output would coincide. So since we have m number of AVs, this term appears for those AVs, and this term would appear for representing the human driven vehicles dynamics with the n minus m number of human vehicles. And in order to compute the eigenmodes of this linearized dynamics, we can compute the 2n roots of this actually equality. You know that if we simplify this equality, we would get a polynomial of order 2n. So finding the 2n roots of that polynomial would give us the eigenmodes of linearized dynamics. This is the exact way to define the string stability based on the definition that we previously provided. So we know that the 2n roots of this equality lie in a curve defined by this equation. So gamma is defined as the AV penetration rate, the ratio of the number of autonomous vehicles to the total number of vehicles. So we know that finitely many numbers of points, those 2n roots, should lie in this curve. So here, the idea of some sufficient string stability condition automatically comes to our mind. So rather than imposing 2n memberships for those 2n roots, we simplify the conditions by automatically imposing this condition, imposing that the whole curve lie on the left half plane. So that's why the results based on the string stability criterion in this paper and the previous research works are somehow conservative. But the advantage is the simplicity of deriving some theoretical results. So defining this transfer function, we realize that such a sufficient string stability condition is equivalent to the norm of this transfer function less than or equal to 1 for all the frequencies And that one is based on the definition of the H infinity norm equivalent to the H infinity norm of H gamma of S less than or equal to 2. So through this paper, we will utilize this strength stability criterion to derive our results. So here we see equivalent actually derivation in order to derive the propositions and corollaries by taking the logarithm from the h gamma of I omega, we reach to this equivalent term, which is some sort of linear term, 1 minus gamma times the alpha of omega plus gamma times the beta of omega. This term represents for the system's dynamics, and this term represents for the controller, AV controller's dynamics, actually. And we can realize that the H infinity condition is equivalent to the non-negativity of this term in terms of alpha. And similarly, for the beta, uh, this condition is equivalent to the non-negativity of delta of beta. So here we see some trivial equivalences. The norm would be less than or 1 if this term would be less than or equal to 0. It's just by taking the logarithm. And without loss of generality, we can just consider the non-negative part of the frequencies because we know that this holds. And our equations are invariant with respect to taking the square. So one can verify that in the case of worst case scenario, when the delta alpha is negative, meaning that here, if this is negative, then for some frequency, this stability condition would be violated. So we need to characterize that scenario mathematically, which is like this. We need to find the sign of d alpha of omega. So for this interval, the d alpha of omega would be non-negative, but outside that interval, it would give us negative values. So this is one of the main results of the paper, this proposition. It says that considering the worst case scenario for which the human driven vehicles dynamics violate that is string stability condition for some frequencies, then in that case, the string stability criterion holds for control parameters if and only if the delta of beta, that polynomial-like term in terms of beta would be non-negative, and also this inequality should be satisfied, which gives us a lower bound depending on beta for the AB penetration rate. So how to compute that J star of beta? It's just finding the infimum of this function, which is a function of frequencies, over the finite interval that we characterized via determining the signs of d alpha of omega. So if we plot that function in that bounded interval, it is like a parabola starting from this finite value, then going towards the infinity when we get close to this frequency, and some frequencies in between could be detected if they are minimizers or not by just imposing, the first derivative condition and also the curvature condition for that, so that it guarantees that it is minimum. So in the next step, we parameterize the constraint sets consisting of the rational driving constraint sets and also the box constraint sets and the string stability condition that we got here, the non-negativity of delta of beta. So in order to parameterize those sets, we need to take the intersection of those B1, B2, and B3. So first of all, we parameterize the sets of intersection set of B1 RDCs and the string stability. To that end, in the following proposition, we systematically incorporate the box constraints. But first step is that the intersection of B1 and B2 could be parameterized as these parameterized sets in terms of these positive and non-negative parameters. So in this other main results of the paper, we state that the parameters P, Q, and R satisfying box constraints can be parameterized via the parameters psi1 up to psi3 with a simple idea that we write them as the linear combination of some, coefficients that they vary between 0 and 1. So we detect the lower and upper bounds for each of them, PL, PU, QL, QU, and RL and RU. And then form the linear combinations of those actually lower and upper bounds.
Hey, MirSaleh, just a time check. We have 10 minutes left, then it'd be nice if we can also have some Q&A and discussion.
Okay, so sorry about that. I was kind of slow then. Uh,
You can always read the paper for some of the details, so I suggest focusing on like the core results.
for sure, for sure. So let me actually present those choral results. So the choral results are that we derive these lower and upper bounds that when we are given the number of human-driven vehicles, then this inequality presents the optimal minimum number of the required autonomous vehicles to stabilize traffic flow. And also, equivalently, given the number of autonomous vehicles, this inequality gives us the optimal maximum number of the human-driven vehicles. So for the special case of a single AV, we get upper bound on the number of human-driven vehicles, unlike the scenario considered in the unconstrained scenario in this highly related paper that they were saying that we can stabilize any number of human-driven vehicles. The reason was that they were not considering any upper bounds on the controller gains. So these are some of those illustrations showing the dependency of the AV penetration rate on the upper bounds and lower bounds that we have incorporated. And also one point is important here that although enlarging the constraint intervals make the smaller optimal lower bound on AV penetration rate attainable, but it leads to a slower transient response due to the fact that this dominant pole would get closer to the origin, actually. And here we show that, without any autonomous vehicle, the system is unstable because these eigenmodes are on the right hand half plane of the on the right half plane. But by adding just a single AV, we show that we can stabilize those eigenmodes and put them all on the left half plane. So here we see some trajectories corresponding to the second HV and the n-1's HV. So this one shows for the second HV, which is the worst one, because for that vehicle, the perturbation has been amplified through the dynamics, but for the n-1's HV, the AV has stabilized that amplification by the controller design that we have proposed. And utilizing this quantity, this H-infinity based measure that we define, we find the suboptimal distribution location of the AVs as 1, 9, 17, 21, and 25 for the case that we have 27 human-driven vehicles plus 5 autonomous vehicles. So I already mentioned those main remarks. And as some future directions, we can consider nonlinear models with large perturbations that would give us more realistic understanding of the proposed method, and generalizing the results for the case of multi-lane mixed vehicular platons via incorporating the hybrid system stability analysis techniques. Here is some of our recent works that we have done on autonomous vehicles topic. And this work was supported by the National Science Foundation grants. And also we would like to thank Professor Dan Work for his valuable suggestions on the numerical simulations parts. So thanks for your attention. Thank you so much. So if you have any questions, I would be happy to hear your questions. Thanks.
Any questions from the audience in person or on Zoom? June, go for it.
Okay, I think you can hear me.
Your laptop?
I should mute myself or
This device in the middle of the room will grab you.
could you come back to the result page? I think I missed a part right here.
Which page? Sorry.
The result of like the number of autonomous people should be larger than some.
Okay, got it. Sure.
Yeah,
This slide. Okay.
always like is J out of 2 star here. I don't.
Okay, what is the J star double star? Yeah, I could not show it because it was actually given in this corollary. We can find the J double star via maximizing the J star of beta, parameterized beta, over the parameterized spaces. So here in this corollary, we propose how to get the parameterized set depending on parameters theta 1 up to theta 3. And those parameters would be imposed by these sigmoid functions. So we would get some unconstrained optimization problem searching for the maximization of J star of beta, and J star of beta was given as here, as I showed you. So maximization over that space would give us the value of J double star. And actually J double star appears in the denominator of the lower bound for the AV penetration rate. So by having larger value for that, we would get better minimum number of the AV autonomous vehicles.
Or you just say that the J star is like come from the unconstrained optimization, and how about J2 star? Could you repeat it? Sorry.
I said that we can find the J double star by finding the maximal value of this optimization problem, because this optimization problem is constructed based on the parameterization of the whole set search space, I would say. So firstly, we incorporate all those constraints, and then we map them to find this unconstrained setup. Then we actually employ some solvers like fmin search in MATLAB, which is a Nilder-Mead simplex-based method. So the advantage of doing this is automatically we impose all those constraints rather than getting worried about the satisfaction of those explicit constraints like the previous method in the other research work.
And you flashed by it quickly, but you showed an example of that calculation, I think for like 5 AVs.
Exactly.
Maximum number of human vehicles was like 23 or something.
Exactly over here. So we have found it exactly. So J double star is about 5 and 5.5. So it would give us the maximum number of 27 vehicles for the human-driven vehicles that we have shown here by red vehicles. That and the suboptimal distribution of the AVs for the locations, we have found these locations that they are somehow close to uniform distribution. I remember that for the m equal to 4, it was giving exact uniform distribution. So it depends. Hopefully, in the next steps, we would explore how we can actually improve the performance of that greedy algorithm as well.
Yeah. Maybe one more question?
Sure.
Maybe I'll ask real quick in this framework, the dynamics of all the human vehicles are uniform. Is that correct?
For this setup, yeah, they were all homogeneous, uniform. That also simplifies the calculations. But regardless of that, we can consider different dynamics for the HVs and try. But the thing is that, let me show this condition would take a different form. Here, since we have, homogeneous dynamics, it is just G. For the scenario that you mentioned, it would be G1, G2, up to GR, for example, up to some levels. It would make the setup more realistic and more complicated meanwhile.
Maybe I'll ask one more question. So you mentioned the optimal distribution of the AVs is uniform. In the example you showed us at the end, though, it of course wasn't perfectly uniform.
It was not, exactly uniform, but since it is suboptimal, it is computed based on greedy algorithm, not based on the exact search brute force method. So that's why. So if we search the, exact solutions, probably this vehicle could be, shifted to the other part, change the distribution. Actually, the distribution could be changed, I mean, because the solution provided by the greedy algorithm is suboptimal due to the computational difficulty. We cannot compute all the multiplications, because in order to find the suboptimal distribution, we have formed all those multiplications subsets actually on the road. All those combinatorial multiplications have been considered. If we want to compute all the values exactly for each setup, it would take millions of scenarios. So that's why probably we don't get the exact uniform distribution based on our intuitive actually guess, That's the thing actually.
Two quick comments is, number one, if you were to hand place those 5 AVs in a uniform way, I'm curious if then you calculated the objective function. It seems like a H infinity norm something. Then I wonder if it would be even less than your suboptimal solution.
It's actually it's a good idea. Actually, I had not thought about this. I would re-examine it and I will let you know the result.
Yeah, and then
But
given
good
the
idea.
complexity of calculating this for every variation of where you place the AVs, rather than a method to optimally solve that, it'd be really nice if there was some theoretical result that said just the uniform distribution was optimal. And then some suboptimal greedy algorithm is apparently not necessary, because you can just, it just says what you think is intuitive is correct, and you don't have to work harder than that.
Mm-hmm. And also another point that I wanted to mention is that due to the simplification, most of the methodologies employ the sufficient string stability. H-infinity based one. But the exact methodology would be based on the definition, computing the 2n roots, the eigenmodes. And in order to compute those eigenmodes, we can construct 2n by 2n matrix and, find the roots of that matrix, probably find the spectral abscissa or that sort of things in order to impose the string stability in a less conservative way. That's also another idea that I want to somehow explore in the future.
Okay, wonderful. Let's give MirSaleh a hand.
Thank you so much. My
Thank you so
pleasure.
much. This is really great for us.
It was my pleasure. Thank you so much. You can contact me via email if you have any questions. I would be more than happy if I could answer some of your questions. And also, please go through the archive version because the letter version is just 6 pages without proofs. So in the archive version, we have proposed all the details actually.
Makes sense. Okay. Thanks, everybody.
Thank you so much.